What if we could power our entire civilization with a clean, safe, and virtually limitless source of energy? What if we could replicate the very process that powers the sun and the stars right here on Earth? This is the promise of nuclear fusion, the long-held dream of a future free from the environmental burdens of fossil fuels. But turning this dream into reality means conquering some of the most extreme engineering challenges humanity has ever faced. At the heart of this challenge is a number: 100 million degrees Celsius. That's hotter than the core of the sun, and it's the temperature required to make fusion happen. Containing something that hot is, to put it mildly, difficult. And for decades, the struggle to manage this colossal heat has been a major barrier on the path to fusion power. But now, an unseen guardian, a sophisticated artificial intelligence, is changing the game. This is the story of HeatML, an AI shield that is helping us finally tame a star on Earth. The dream of fusion energy is rooted in simple physics. When you take light atomic nuclei, like isotopes of hydrogen found in seawater, and you force them together under immense pressure and heat, they fuse. This fusion releases an enormous amount of energy, far more than any chemical reaction, and it does so without producing greenhouse gases or long-lived radioactive waste. To achieve this on Earth, scientists have developed a device called a tokamak. Imagine a giant, hollow donut wrapped in some of the most powerful magnets ever created. Inside this donut-shaped vessel, hydrogen fuel is heated until it becomes a plasma, a superheated state of matter where electrons are stripped from their atoms. The powerful magnetic fields are designed to act as an invisible bottle, confining this 100 million degree plasma and keeping it from touching the walls of the machine. But here's the problem. The bottle leaks. Even with these incredible magnetic forces, the edge of the plasma is a turbulent, chaotic place. Bursts of intense heat and energetic particles can escape the magnetic cage and slam into the inner walls of the reactor. These inner surfaces, known as plasma-facing components, are subjected to an energy onslaught comparable to what a spacecraft experiences during atmospheric re-entry, but continuously. A particularly critical area is a component at the bottom of the tokamak called the diverter. The diverter acts as the reactor's exhaust pipe, designed to handle the bulk of the escaping heat and particles. It is, without a doubt, one of the most challenging environments in all of engineering. If the heat flux in any one spot becomes too concentrated, it can melt or erode the diverter's protective tiles. This not only damages the multi-million-dollar component, requiring a complete shutdown for repairs, but it can also release impurities into the plasma that cool it down and extinguish the fusion reaction itself. For decades, predicting and controlling where this intense heat will land has been a central focus of fusion research. The complex, three-dimensional geometry of the reactor's interior, combined with the twisting, intricate paths of the magnetic field lines, creates very specific patterns of heat deposition. Think of it like a complex arrangement of objects casting shadows in a room filled with light. In a tokamak, some internal components can cast magnetic shadows on other parts of the wall, shielding them from the direct blast of the plasma. Knowing the precise location of these safe, shadowed regions is absolutely critical for designing a robust and long-lasting reactor. For years, scientists have relied on a powerful open-source computer program called HEAT, which stands for Heat Flux Engineering Analysis Toolkit. This program meticulously traces the paths of magnetic field lines from every point on the reactor's inner surface. It checks to see if a field line is blocked by another component before it can hit a surface. If it's blocked, that area is marked as being in a magnetic shadow. Heat is incredibly useful, but it has one major drawback. It is painstakingly slow. Because it has to perform such a detailed analysis of the complex 3D geometry, a single simulation to map out the shadows for one specific magnetic configuration could take around 30 minutes. Now, 30 minutes might not sound like a long time, but in the world of engineering design, it's an eternity. If you want to test a small change in the shape of a component, you have to wait half an hour for the result. If you want to explore thousands of possible operating scenarios to ensure your design is safe, you're looking at months of computational time. This created a massive bottleneck, slowing down the entire design process for new fusion devices. And as for using it during an actual experiment, forget it. You can't control a plasma that changes in microseconds with a tool that takes half an hour to think. This computational roadblock is precisely the problem that a team of brilliant researchers set out to solve, and their solution is poised to revolutionize the field. It's called HeatML. The ML, of course, stands for machine learning. HeatML is the result of a powerful collaboration between some of the biggest names in fusion. Commonwealth Fusion Systems, a dynamic private company spun out of MIT, the U.S. Department of Energy's Princeton Plasma Physics Laboratory, or PPPL, a world leader in fusion science, and Oak Ridge National Laboratory, another DOE lab with a rich history in nuclear technology. This project was specifically created to support the design and operation of Spark, a compact, high-field tokamak being built by Commonwealth Fusion Systems. Spark is designed to be the first machine in the world to achieve a net energy gain from fusion, producing more power than it consumes. Its success is the critical next step towards ARC, their vision for a commercial fusion power plant. The team recognized that the 30-minute wait time for heat simulations was a major obstacle for the rapid development of Spark. They needed the same crucial information about magnetic shadows, but they needed it almost instantly. So they turned to artificial intelligence. HeatML is what's known as a surrogate model. It's an AI that is trained to mimic or act as a surrogate for a more complex and time-consuming simulation. The team used a deep neural network, a type of AI with many layers of mathematical operations that is exceptionally good at finding complex patterns in data. To train it, the researchers ran about 1,000 simulations using the original, slow heat code. They fed the AI the inputs, the specific magnetic field configurations, and the outputs, the final 3D maps of the shadowed regions. The AI's job was to learn the relationship between the two. After this training period, the results were nothing short of transformative. Once trained, HeatML can generate a complete shadow mask in a matter of milliseconds. Let that sink in. A process that once took 30 minutes now happens in the blink of an eye. This is a speed-up of several orders of magnitude. It's a quantum leap in computational capability. This dramatic acceleration has profound implications. For engineers designing the reactor, it means they can now run tens of thousands of simulations in the time it used to take to run a few dozen. They can rapidly iterate on designs, explore a much wider range of operating conditions, and optimize the components for heat management with a level of detail that was previously impossible. But the most exciting possibility lies in real-time control. The incredible speed of HeatML means it can be used during a live fusion experiment. The AI could constantly monitor the plasma conditions, predict the heat load on the diverter in real time, and if it detects a potentially dangerous hotspot forming, it could automatically trigger adjustments to the magnetic fields to steer the heat away from vulnerable areas. It's like giving the reactor a nervous system with superhuman reflexes, allowing it to protect itself from its own immense power. As Michael Churchill, a key scientist on the project from PPPL, explains, this research opens up fascinating new avenues for control and scenario planning. This breakthrough is a testament to the people behind it. The lead author of the paper on HeatML is Domenica Corona Rivera, an associate research physicist at PPPL. Her expertise in developing real-time magnetic controllers for plasma shape was instrumental. She understood the core problem intimately. If the plasma melts a component, you have to stop operations, which is the worst-case scenario for a future power plant. Her work provides a direct solution to this critical threat. This success story is also a showcase for the power of collaboration. You have PPPL, with over 70 years of foundational fusion knowledge. You have Commonwealth Fusion Systems, bringing the agility and commercial focus of the private sector, providing a clear, real-world application with their Spark tokamak. And you have Oak Ridge National Laboratory, contributing its vast expertise in materials, supercomputing, and nuclear engineering. This public-private partnership demonstrates a new, accelerated model for tackling the grand challenges of science. But the story of AI and fusion doesn't stop with HeatML. This is just one powerful example of a much broader trend. Across the globe, AI and machine learning are being leveraged to solve a whole host of problems in the quest for fusion energy. AI is being used to optimize the fundamental design of reactors, sifting through millions of potential configurations to find the most efficient and cost-effective designs. It's being trained to predict and prevent plasma disruptions, sudden, catastrophic losses of plasma confinement that can damage the reactor. AI controllers are learning to manage the plasma in real time with a level of precision that human operators could never achieve, making thousands of tiny adjustments every second to keep the fusion reaction stable and optimized. AI is even accelerating the discovery of new materials, predicting which alloys and composites might be able to withstand the brutal environment inside a reactor. Fusion experiments generate petabytes of data, far too much for humans to analyze effectively. AI algorithms can sift through this data, uncovering hidden patterns and new physical insights that advance our fundamental understanding. Experts in the field are incredibly optimistic. They see this synergy between AI and fusion research as a critical catalyst, significantly accelerating the timeline for when we might see commercial fusion power on the grid. Right now, HeatML is a specialized tool, perfectly tailored to the unique geometry of the spark diverter. But the vision for its future is much grander. The team is working to generalize the AI, to create a universal shield that can be applied to any part of any tokamak, anywhere in the world. Such a tool would be an indispensable part of the engineering toolkit for the next generation of fusion power plants. The development of HeatML is more than just a story about a clever algorithm. It's a story about human ingenuity and our relentless pursuit of a better future. It's about how the abstract, digital world of artificial intelligence is becoming a physical shield, helping us contain the power of a star. As we stand on the threshold of a new energy era, tools like HeatML are the silent guardians, making the dream of fusion a tangible reality. With every hotspot it helps prevent, with every millisecond of calculation it saves, we move a crucial step closer to a future powered by clean, safe, and truly limitless energy. The path is still challenging, but with AI as our guide, we are navigating it faster and more safely than ever before.